Good evening and welcome back to Vegas October 1 Sounds. Tonight I'm going to be doing a kind of a technical video, and for the next 2 or 3 videos I'll be going along the same topic. What I'm going to introduce you to is an online interactive simulation gadget put out by the University of Colorado at Boulder. And this one in particular, there are dozens of them that they support there, deals with waves and the interactions of waves, and it covers both light and sound. It actually does some experiments with water. And with the sound portion of it, it delves into the implementation of sound from a molecular level. And so rather than me creating a gadget that I could have you run on your machine, I thought I'd just let everybody have let everybody have access, but introduce you to this thing which you can use. The link to it is in the description below, and when you type that into your browser, you'll end up at a place that looks like this. Now I'm going to do F11 on this and get it full screen, so I can have the advantage of this full screen. And the 3 or 4 videos that I'm going to be doing on this correspond to the 3 or 4 different sections that they have broken their experimental laboratory into. And you might ask, well, why this and why now? There's a gap in the understanding that I've presented with regards to sound and the impact of that understanding on how we perceive the Vegas shooting. And that gap has to do with what's happening at the very lowest of level, and the gap also includes very little visualization on how sound waves interact. I've said a lot of words, I've drew a lot of diagrams, but I've never put it in a visual way that is easy to, I believe, comprehend. And that's what these little laboratory experiments are going to do for us. So that by the time you're done with the 3 or 4 of them that I'm going to do, you'll be able to address some questions that are being raised about the Vegas shooting with great ease. So, for example, one of the questions you'll be able to answer is, what happens when I put multiple speakers into an environment both broadcasting the same sound? And I point out this question because multiple people have said that the sound that night for gunshots was faked, and that always boils down to some sort of magical device that they're saying can be used to simulate the sound. Well, after we go through this set of experiments, you'll see in very explicit and a visual way why that's entirely impossible. And so that's one of the nature of the questions. You'll also have a very good understanding of how sound propagates. At a very small level, you'll see the impact at a macroscopic level, and then we can talk realistically, more realistically anyway, about what's happening in Vegas. So, that's the impetus of these little things. Now, I want to assure you that there's no math involved in the next 3 hours. And by no math, I mean, if you've got a calculator, the most I'm ever going to do is multiply, divide, and square root. So, without any further ado, let's go ahead and start, and let me introduce you to the interface to these little applets or gadgets or whatever. So let's start with waves. Here we see, and this of course is my drawing tool over there, it's not part of the applet, that we have a little area over here where we have symbols and something that looks like a pipe and whatnot, and all these things are clickable. So for example, I can click the pipe and out will come a drip, and based upon how you have configured all the other things, certain things will happen. For example, to the left here we have we can either generate a single pulse or a continuous drip. So if we put it on single drip and hit this little green thing up there, the pipe emits one drip, and out comes a wave. if we wanted to look at this, we've got it on water. So if we look at this from side view, that was a top view. Then we do the same thing, and we can get a nice little graphic of what's going on from the side view of the perspective of the water. And so we've looked at this little button, we've looked at these two little areas, continuous or pulse. We can stop or play. Nothing's happening there, so let's see. Let's go ahead and turn it on, and if we pause it, you can just pause it midstream, or you can step it forward slowly, or you can let it go continuously but slow it, normal, all these good things. Now up over here are controls that allow us to change the rate at which the drips are coming out of the faucet. We call that frequency. So if I bump it up to the max and watch, you can see that the drips come out further. And if I drop down there, they come out slower. And we can change how much energy is associated with each drip, i.e. the amplitude. So if I drop it down to there, the waves get smaller. To over the max, they get max. We can also put a graph on there, which diagrams the height of the waves. I don't use that too much, but okay. Now, not only can we do it with water, we can do something similar with sound. So let's just do continuous, and we have a few more options over here. And or we can do it with light. And again, I'm clicking that button to turn it on. So let's go back right to the very beginning now that I've introduced you to some of the tools. Oh, and the other three tools up here, these are draggable. This is a measuring tool. You can drag it around and measure distances, from point to point. This is all in metric, so we'll be dealing with, in this case, nanometers, which are 1 by 10 to the minus 15th in seconds. We have another thing up here, which is a graph thing, which has two measuring devices. I can stick them over here on that, anywhere I want, and that way I can compare two, let's put them a little bit further apart, two different positions at the same time. So let's go ahead and turn that off, or we could have stopped it down here too, and get back to the water and turn everything off. Let it settle down, and put these back up in their position because I don't need them. And this last one was just a timer. So I don't think there's anything else I need to do. No, okay. So let's start talking about waves. What we have is a side view here of a water drop that hits the surface of a pond, or anything of water, and because of the weight of that water causes dispersion or displacement. And so if we do a single pulse, we can see that, now we can stop that the pulse, and you know what, let's do it again and take it step by step. The water starts to come out, hits the surface, the weight of the water accelerating down makes a depression in the water, and it reaches a point where it has expended its energy, and then the water, because of the surrounding pressure, pushes itself back up. But oh, we're not done. It created a splash, and up it comes, and then back down until it all settles out and evens out, and then that wave it produced propagates to the right. Now in this case, what we have is a transverse wave, and that is, the wave is, well, that's not a very good color for that, is it? The wave is going from the left to the right. Okay, but the amplitude of the wave is going top to bottom, so it's at a right angle. And that's what we call a transverse wave. And there are two forms of waves that we'll be talking about. One is called transverse, and one is called compression. And sound can be carried by either But for the most part, in our normal dealings with sound and air, we're going to be talking about compression waves. But we start by first understanding what is a transverse wave, namely that the propagation direction of the wave is perpendicular to, or normal as they would call it, to the wave displacement. Okay, so let's get that out of our way. All right. What are some other things here that we can observe that make a lot of sense? All right, let's talk about frequency. Let's just let this thing run on a continual basis. Clear out, and then we'll let it run on a continual basis. And as we see, it produces a continual set of waves. Now we'll notice that the wave height over here, or the wave amplitude as it would be called, is different than at the source. And the faucet is what we call the source. And it's substantially different. And that's important to keep in mind because the nature of the energy being departed from the droplet is transformed into what the medium, in this case water, is capable of doing. That is, the water is not capable of completely responding to the impact of that droplet on the surface in a way which preserves all of the aspects of that interaction. But so overall it tends to even out into what we call a sinusoidal wave, and those sinusoidal waves are measured. If we measure them, if we measure from, well, let's do something else first. Let's put back over here. From peak to peak, which are the high points of the amplitude, we have one complete cycle, and that's called the wavelength, typically lambda or wavelength. And we measure that either in distance or in time. So for example, since this is a 1 centimeter scale up there, this would be a little over 1.5 centimeters between the peak and the peak. Correspondingly, these are the troughs, and the same, it could be measured there from trough to trough. Or if you were to, draw a line down the middle where it crosses it, you could measure it from where it crosses it also, from crossing to crossing. Either way, if the wave is symmetrical in all regards, then you're going to come up with the same answer. And the frequency is nothing more than 1 over the wavelength. So, times the speed of the propagation, of course. So if we lower the frequency, and let's pull this back over to our jobber two. If we turn this thing running again, and we slide, and we notice that we are at max frequency now, as we slide it down, we will notice then that the wavelength increases, or there's a much larger gap between the peaks and the valleys. So as the frequency goes low, the wavelength increases. As the frequency goes high, the wavelength decreases. All right. That all makes sense, I believe. Now, let's do something else. Let's speed up the frequency a little bit. Takes a while to catch up. Bring down our measuring tool and measure the amplitude. So let's measure the amplitude right under the faucet. I did say right. Well, in this case, we can right under the faucet. All right, there we go. You notice it's off the scale, and then we'll measure it over here somewhere. And you'll notice it's much smaller. So the further, let's see, so what is it somewhere along in between? Let's put one there. Well, let's put one way over here, and then one in between. So the further away from you get from the faucet, the lower the amplitude of the wave. And how much lower is a function of the medium, which in this case is water, and it can oftentimes involve a complex formula. But in general, the further away you are from the source, the lower the amplitude of the wave will be. All right. If we were to look at this from a top view, it would look completely different. We wouldn't see the amplitude because the amplitude is, looking straight on top of it. You just don't see much. What you see are a bunch of waves. Now, if we measure it, then we still have the same graph. But in this case, those little ripples of water look like concentric circles. And this is how the energy spreads out from that drop. And in this case, it spreads out in all directions equally without preference. So as long as there's not some external force operating upon this source, then the energy tends to even out or propagate in all directions. We can model these things as a point source, and we often do call this a point source. And a point source in sound anyway is nothing more than a source of sound which has a propagation mode that looks like a sphere, and it is equal in all directions. Now that's an idealistic model, and nothing is truly ever ideal. And in fact, as we saw earlier here from the side view, while it may propagate out in all directions, it certainly isn't the same at every point, the amplitude that is. And that's going to become a real interesting concern later on as we get into multiple sources. So far we've talked about water. Let's move over to sound and get these things out of our way for the moment. And see what the skinny is. Turn this off. Move over to sound. And start it running. Turn it off. Okay, now in this case you'll notice that the scale up here changed. In this case we have units of time measured in milliseconds, or 1 by 10 to the minus 3, or 1,000th of a second. And the wavelengths will be measured in units of centimeter. So now we're talking about sound. We're talking about sound in air, and the source of the sound is a speaker. And so if we once again look at it at the top view, and we let's move this up here for the moment, and we start it running, which it is, and then we allow it to do sounds here, and we'll start low on the frequency, and we'll start kind of low on the amplitude. Okay, in this case now, the dark regions represent areas of low pressure, and the lighter regions represent areas of higher pressure. And this is caused by the vibrating in and out of the cone of the speaker. And just like the water, at least it would appear, is that the energy from the speaker radiates out in all directions in a fairly evenly distributed form in concentric circles. And if we were to pull down our measuring graph here and measure it, let's see, we can measure it here, and we can measure it over here, and it's not quite in phase. Oops, wrong direction. There we go. We can see that they're about the same amplitude there. And once again though, as we pull to the right, we should see our amplitude drop. In this case it's not quite so prominent, so let's stick it there in the middle, and there you can see that one is substantially larger than the other. So again, we have the same property as with water. The further away you are from the source, the lower the amplitude of the disturbance. Now the medium for carrying the sound wave in this case is air. Sound can be carried in any medium. It can be carried in water, it can be carried in wood, it can be carried in steel, it can be carried in gases, it can be carried in ice, snow, your body, everything. And the medium determines the rate at which the energy is dispersed. And the more dense or heavier inertia that the medium has, the quicker the sound propagates. So a gas has some of the slowest propagating speeds for sound of any material. Heavy metals that are tightly bound, like steel, have a very fast propagating speed. Rocks have a very fast propagating speed. So a general rule of thumb for air is that the sound, propagates at 343 meters per second at room temperature at sea level. And that, just as a rule of thumb, I use, 1 foot per millisecond for propagation speed. It's not entirely accurate, but as a rule of 10 roughness, it's close enough. So for every 1,000th of a second in air, sound will propagate for 1 foot. Now, this is all good and well. On the top view, let's take it to the side view. Well, unlike water, sound does not have a transverse wave when viewed from the side. Sound is a compression wave. That is, you have regions here that are high density, and then they propagate to the right in low density, and the energy is going to the right, and the amplitude goes to the right. So we have what's called a compression wave. When the propagation direction is the same as the disturbance direction, then you have a compression wave. And we can best see this if we look at it from a particular particle representation, which fortunately this little gadget will do. So if we switch over to particles, this is what it looks like with all the atoms. And you can see here that, well, there are regions where over time the particles come close together and then they come further apart. The high pressure regions correspond to the particles being close, and the low pressure regions we'll just pause this for a second. Now that wasn't a very good spot, but trying to do one where it's easy. Yeah. So right along close to this, very much close to the speaker at this point in time, there's a low pressure region, high pressure region, a lower pressure region, a higher pressure region, a low region. And so the sound propagates through this by compressing the molecules, which aren't free to roam around. They are connected to each other in an elastic way, and so the molecules only move for a short distance, and then they start to gradually be pulled back to where their original position was. So even though the energy of the wave is propagating from left to right in great distances, the molecular movement is radically smaller. And you can see that here by watching these little red things. And those are put there just for a visual cue. That is, let's play it. And if we bring down this measuring tool here and draw a line straight down, and then place it right over, one of these things, you can see that the little red dots do not deviate by very much from the line that goes up and down. But yet, if we put the waves in here, let's do both of them. The waves, which are the model for the energy propagation, go from the speaker to the right at distances much greater than which the molecules are moving. So this tool is great for visualizing what's happening. It allows you to look at the particle level and kind of get a grasp for what's happening in the air. And so the actual physical molecules that receive the energy from the source or disturbance that causes them to move, those molecules stay relatively firmly in place depending upon the medium. With air, they're freer to move around than they are in steel. For example, in steel, the average distance they move is much, much, much smaller than the average distance they can move in air, because air is a compressible medium. Now remember, air is not homogeneous. Air typically consists of, many different things: water vapor, hydrogen, methane, ozone, nitrogen, oxygen, all these things. And each of those molecules are different in shape, they're different in weight, they're different in elasticity, they're different in how they interact with their neighbors. And so when we talk about the speed of sound, we have to take that into consideration. We also have to take into consideration another factor, and that would be temperature. So let's put this tool back up there. Let's stop this thing. Well, first off, let's turn it off, let it run so it all clears out. That is, we don't want the speaker generating any sound. And here you'll notice that the model has these molecules still moving about. And this is typical of a gas. That is, the temperature at which the gas is dictates how far these little things vibrate around. The higher the temperature, the more energy there is, and therefore the greater the vibration. And because the vibration is greater, they collide with one another faster, and therefore they can transmit energy from one to the other faster, and therefore as the temperature increases, so does the propagation speed. And it's important to keep in mind then, we're not talking about molecules moving vast distances, we're talking about molecules moving small distances and then snapping back to their original position, or even overcompensating and heading. So if we start this up again and we follow just one little red dot here, you can see that it moves to the right, then gets snapped back, maybe overshoots, and repeats the whole process over and over and over. You can also, on this one for sound, you can play the tone, which I just rarely do. So in this case, the tone is a monotonic, and you can change it from lower all the way up to, I think about 1 or 2 kilohertz. But I rarely have the sound playing. Sometimes I'll use the graph portion here to show me what's happening, because watching those molecules or those fuzzy waves is not real clear. But here on the graph, and we could have done that by pulling one of these measuring tools over also, except it kind of goes off scale. So here you'll notice once again, and we're going to make the amplitude larger by sliding this across. Let's make the amplitude large. Is that the shape of the wave directly in front of the speaker is substantially different than the shape of the wave at a distance away from the speaker. This up close it's narrower and higher, and out there it's further apart and lower. Now in general, let's just stick with waves here. In general, that there is a distance at which, and that's normally about, well, I'm not going to say how far it is. There is a distance away from the source of the sound in which the waves stabilize. And then they keep the same shape, relatively speaking, for large distances. However, with a gas, there's always some energy being dissipated into the gas just to move the molecules around. And as that energy dissipates, the wavelength does spread out. So this wavelength here, if you were to view it 1,000 or 2,000 or even a mile away, would increase slightly. So the frequency doesn't stay the same, and that's what we call attenuation. And the higher the frequency, the more attenuation there is per meter or cubic meter of the gas. So if we start out with a 10 kilohertz signal and we travel a mile, it's going to be much more attenuated or reduced in intensity over what the distance would predict. And so, as a real example, when you hear a supersonic crack, which tends to be dominating at 1500 hertz and above, at large distances, yes, you can record these things at large distances. Half a mile away is what they are recorded in Vegas. Actually, more like 1,000 feet. Let's call it 1,000 feet. 1,000 feet away from the bullet, the supersonic crack in a quiet background is recorded on a tape and can be analyzed. But when it gets to the recorder, it has lost almost all of its high frequency component, and it starts to look like a muzzle blast, which is a much lower frequency event. So you have to keep these kind of things in mind when you're performing audio analysis, because at large distances away from the source of the sound, the frequencies are changed. Not that they aren't changed by other things too, like the tape recorder itself, which has a preferred frequency equalizer applied to it. But we'll talk about that in another video. So anyway, over here, turn off the graph, and we'll get back to these little particles and everything. Alright, and once again here too, even in sound, you can measure these things. You can measure it from peak to, well, let's go from that peak to that peak, and that would be 154 centimeters. There's 2.54 centimeters to the inch. Okay, so for every 25 centimeters you have 10 inches. So in this case, how many multiples of 25 do we have? We have 6, or 150 centimeters. So for this low frequency sound, then the wavelength would be this distance, which would be 6. Let me make sure I'm doing that right. Let me bring up my calculator. So 157.4 centimeters divided by 2.54, or was it 2.4? I think it's 2.54 equals, oh no, that's 61. Yeah, see, I knew I got a factor of 10 off there. So this sound has a wavelength of 61 inches, which is about 5 feet. So the wavelength of sound at the lower end is large, and that will become very important when we start talking about interactions of waves. Alright, so what is the wavelength for the higher frequency? Well, if we turn this back on and we run it up to about 2 kilohertz, and then when it gets full there, we can measure it again. Poof. Alright, we stop it. We put it right in the center. We'll measure down to the center of that one, and we get 67. Which, if we bring up our calculator, or another version of it, I don't care, 67.7 centimeters divided by 2.54 centimeters per inch, and we're going to get 26 inches. Okay, now that's only up for 2 kilohertz, but that's the typical range of a muzzle blast, from a few hundred to 2,000 or less. So in that case, we're going to have a wavelength that varies from 5 feet to a little over 2 feet. Alright, so if we go all the way up to 10 and 20 kilohertz, 20 kilohertz being the upper reaches of the human hearing, then the wavelength gets substantially smaller, down into the inch or sub-inch range. And it's important to keep these wavelengths in mind, though, that we're not dealing with things which, like a microwave, or thousandths of a, or even hundredths of a thousandth of an inch across. We're talking about things which are the size of our body for the lower frequency of our audible range. 5 feet, is the same width as our body, or height of our body. Alright, so we're still talking about waves, we're still talking about sound, and you could do the same thing with light, only in this case the scale is going to be 10 to the minus 15th seconds, and correspondingly nanometers are way small also. But I'd like to stick with sound for the moment, and water. So what have we learned so far? We learned that energy propagates. It forms, from an amplitude perspective, these things called waves. For sound, the waves are compression. that is, the propagation direction and the amplitude changes in the pressure, are the same. That is, it propagates from the source to wherever for a point source equal in all directions, and correspondingly the compression direction of the molecules is the same. Whereas with water we have, and that's called a compression wave, whereas with water we have the direction of propagation of the energy of the wave, in this case left to right, but the amplitude of the wave from top to bottom, and therefore it's perpendicular, 90-degree angle normal to the propagation direction, and it's called a transverse wave. We have learned that we'll be dealing almost exclusively with compression waves when we talk about sound. We've learned that the wavelength for sound varies from 5 feet to down into the sub-inch range. That for the muzzle blast, it's probably somewhere on the order of 2 feet or less. For a 10 kilohertz and for the supersonic crack, since it starts around 1500, it will go from about 3 foot and shorter, and it ended up at 10 kilohertz, or probably less than a couple inches in wavelength. How far will the energy propagate for sound, let's say in 1 millisecond? Well, you take the time that it takes to propagate in 1 millisecond multiplied by the speed of sound, which I said was 343 meters per second, or approximately 1 foot per millisecond, times 1 millisecond is 1 foot. As the temperature goes up for sound, the propagation speed goes up and that distance becomes smaller. What's the frequency? 1 over the wavelength, or 4 unit per that's not a very precise definition. The frequency is actually the number of peaks that cross a specific point in 1 second. That's frequency. And that's a function of the wavelength and the propagation speed. Alright. So, do we need to cover anything else to talk about waves? We also talked about the fact that when the source, in this case a speaker, or in the other case water, imparts its energy initially to the wave, it may be in a completely different amplitude and shape than the form of the wave that will eventually be perceived or propagate forward. We've talked about the fact that over distance, energy is removed from the system, and because of that, the frequencies tend to be mitigated or attenuated downward. And low frequencies travel further because they're attenuated less, particularly in a gas. And high frequencies tend to I hate the word travel, and yet I use it all the time. They tend to propagate further without being modified. Now, if you have a pure tone, back up. Let's back up. Most sounds are not pure tones like we've been talking about. Most sounds that we hear are a combination of many different frequencies and many different amplitudes. So, for example, let's take, as I mentioned, a supersonic crack generated by the supersonic projectile. Somewhere along the path of the bullet, a crack is generated, and it's continually being generated, but we only hear one portion. And we're going to hear a specific portion based upon the geometry and of our location relative to the path of the bullet. So we'll hear one portion of the wavefront that's generated. And that sound typically is a large broadband signal ranging in frequency from typically 6, 10, 12,000 on down to probably at the lower end of about 1500 hertz, particularly if you're any distance. And as that supersonic crack travels a large distance, the higher portion of the crack is consumed, attenuated, and therefore at large distances when it gets recorded it sounds a great deal like a muzzle blast, but softer, depending upon, where the supersonic crack is propagating from and where you are relative to the source of the gun. It could easily be the case that you are very close to the projectile but vast distances from the gun, in which case the supersonic crack would likely be much louder than the muzzle blast, or it could be just the reversed, or it could be equal, or any combination of those above. But just remember that the frequency can change, and therefore where you are, the supersonic crack may sound different. In fact, the muzzle blast loses a little bit of frequency, but percentage-wise less, so it tends to sound the same in terms of frequency, but obviously since the energy of the wave dissipates over the distance, or not dissipates, has to cover more area. Let's talk about that. That's something we haven't talked about so far. Here in the sound, you'll see that the pressure close to the speaker is very, very bright. That's because all the energy that the speaker is being putting out is in a small area. And as that propagates to the right, it has to cover a larger and larger area of these concentric circles. And therefore, the amount of energy per unit distance along that circle produces a lower intensity. And therefore, at larger distance, that energy gets smaller and smaller. And so therefore, while you may hear a sound that sounds quote-unquote similar, in reality it's different. It's different in amplitude, slightly different or majorly different in frequency, and therefore sometimes hard to compare. Now in the real world, a rifle shot, or even a pistol shot, then let's just talk about the muzzle blast, because that's the thing we're all most generally acquainted with, the boom. If you're kind of in front of the gun, even if you're a distance away, you're going to hear a pretty good boom. But if you're at 90 degrees to the barrel at any distance, it's going to sound completely different. So in reality, the muzzle blast is not truly equal in all directions. It's very directional. And so when you're out in the field and you hear a boom and you say, oh, that's a 357 Magnum, you better be careful where you're at, because that actually could have been a 50 millimeter Hauser, right? It's just that you're at such a large angle perpendicular to the barrel of the gun that the intensity of it was much, much softer. Now, that's kind of a bogus comparison, because, howitzer is such a huge gun that if you're anywhere even remotely close, it's going to, blow your socks off. But the idea is the same, is that it's very, very difficult to tell the difference between an M16 or a 30-30 or a .06 or an .08 if you're at a large